All right, let's look at some chain rule stuff. So let's say we have z equal to the inverse tangent of 3x plus 4y squared. And we are also given that x is equal to r squared times t, and y is equal to t times the natural log of r. Sure, that's fine. So we want to find both partial derivatives. We're going to find first del z del t. And then second, we're going to find del z del r. But first, we're just going to write the formula. So del z del t. Oh, before I'm going to write the formula, what do I need to do first? I have to draw the little map thing. So, and kind of following the pattern here. So I know that z is a function of x and y. So z depends on both x and y. And then x and y are both functions of both r and t. So the next lower level, x depends on r, y also depends on r, y depends on t, x also depends on t. You don't have to draw this map. You just have to know all the ways you can get from the top level to the bottom level, essentially. So I'm trying to find all the ways I can get from z to t. Well, I can either go through x or I can go through y. Sorry, like that. So it's going to be del z del x times del x del t plus del z del y times del y del t. In this problem, everything I'm talking about is actually a partial derivative because at every level, the next level down, things depend on more than one variable, right? Z depends on two different variables. X and Y each depend on two different variables. So all of these are correctly partial derivatives. And now we just do the whole thing. So del z del x, we're finding the partial derivative of the inverse tangent or arctangent of 3x plus 4y squared. And we need to know that the derivative of the arctangent of some stuff is 1 over 1 plus that stuff squared. So the derivative of the arctangent of 3x plus 4y squared is 1 over, I wrote this fine, 3x plus 4y squared plus 1. Doesn't matter if you write the plus 1 first or the plus 1 second. I've had people usually write the 1 plus first, but I did it backwards accidentally. And then times del x del t, which is just going to be r squared times 1 plus del z del y, which is also going to be, I missed something here. When I took the derivative of the inverse tangent, I forgot to use the chain rule, the immediate chain rule. It should have been 1 over my stuff squared plus 1, and I said the magic word stuff, so I should be multiplying by the derivative of this inside stuff, which should give me a times 3. So there should be a 3 we're multiplying by. Let's just put it on top here. Then similar derivative for y, for del z del y, we're going to get 1 over 1 plus this stuff squared again. So 1 over, I usually write it as 1 plus the stuff squared, multiplied by the derivative of the inside stuff, but this time with respect to y, so it's going to be 8y. And then multiplied by dy dt, which is going to be 1 times the natural log of r. And again, I would point out you don't really ever want to go further simplification wise, like any simplification at all, really, but you don't want to go plugging in x equal to r squared t and y equal to t natural log of r unless someone asks you to. Also, if you're doing it in web work, control C, control V, right? You can copy and paste and just like copy the function or type it once and then paste it wherever it needs to go. So if it were me, I would actually probably type this out in web work first because it's easier for me to type that visually and then highlight an X and replace it with R squared T and highlight, each X, replace them with R squared T, highlight each Y and replace those with T natural log of R. It's probably an easier way to make sure it like gets input correctly instead of trying to type it all out. Also, I'm sure you're aware, but in case you aren't, it's usually easier to do it like on something where you have a keyboard to type things. Doing the web work stuff on your phone or even on a tablet can be challenging. So do yourself a favor if you can, make it easy to input the things that are terrible to input. All right, let's look at this next one, or the second part. So now we're going to find del z del r. And again, it is a partial derivative. Here's the nice thing about this other one. The first part's going to be the same as it was before. So we're still going to have del z del x, but then instead of del x del t, we're going to have del x del r plus del z del y times del y del r. So we could literally just look at this first part and copy it down. So it's going to be 3 over 3x plus 4y squared squared plus 1 times my del x del r, which is going to be 2r times t, plus my del z del y, which is all of that in parentheses there. It's 1 over 1 plus 3x plus 4y squared squared times 8y multiplied by the derivative of y, the partial derivative of y with respect to r, which is going to be t times 1 over r, or t over r if you prefer. Also, trying to remember. I think last class some people on Zoom tried to ask me some questions via chat, and I totally missed those, and I apologize for that. If you have a question you ask via chat and you don't see me responding to it, feel free to unmute yourself and actually like say words. You might startle me, that's okay, but definitely I felt bad about missing your question. So definitely make yourself heard if I'm not seeing what you're writing in the chat. I'll try to keep an eye on it though. All right. Let's see. I think, yeah, one more thing. So, one more thing. Well, really not one thing. Another thing with this chain rule, which I alluded to before, was that we can use this chain rule formula to then do old 17a implicit differentiation in a much easier way. So this is actually where we're going to do that. So let's take a look at this next part. I would say this next topic is kind of, it definitely gets talked about in class, but it's kind of like just like, here's a neat little thing. And sometimes people will ask you to do it, sometimes they won't. But I feel like your professor probably would. So I don't feel bad like talking about it. So let's go ahead and look at this example. In fact, let me write some words. So the chain rule that we've just talked about can be used as a shortcut for implicit differentiation. So let's look at an example. Let's say we have the equation x cubed plus y squared equal to 7 minus x times e to the y. And we want to find dy dx. So one thing I'll point out is once they've asked you to find some derivative, whether it's a regular derivative dy dx or a partial derivative like del z del y or something, you know two things. You know the variable is the bottom thing. That's the thing that we're assuming is changing, right? You're asking how is the top thing changing as the bottom thing is changing. And also you know which thing is pretending to be the function. So writing dy dx, we know that y is the function and x is the variable. Or if later on I write del z del y, we'll know that z is the function and y is the variable. And anything else that might be in there is we're going to pretend like it's a constant. So here we'll do this. So we're going to do this both ways. So first, the usual way. So we're just going to differentiate both sides with respect to x. So let's see, on the left-hand side, we have the derivative of x cubed is 3x squared. The derivative of my function squared is 2 times my function to the first power times the derivative of my function. All right, we're assuming y is a function of x, so its derivative is going to require the chain rule. On the right-hand side, you're going to get 0 minus, okay, we're going to have to use the product rule here. So we're going to get the derivative of x, which is 1 times e to the y, plus x times the derivative of e to the y, or e to the stuff, is e to the stuff times the derivative of that stuff. And now we're going to do the usual work of solving for dy dx. So I'm going to distribute this minus sign. I have 3x squared plus 2y times dy dx minus equals negative e to the y minus x times e to the y times dy dx. Bringing your dy dx's to the left. So I have x e to the y times dy dx plus 2y times dy dx equal to negative e to the y minus 3x squared. Factor out the dy dx. You're left with x e to the y plus 2y. Still equal to the same. I'm gonna do one extra thing on the right side. Normally you wouldn't need to do what I'm about to do here, but I'm gonna try to make something else more obvious in a minute. I'm gonna factor out the minus sign on the right hand side and have minus e to the y plus 3x squared. And finally divide by that and get dy dx equal to negative parentheses e to the y plus 3x squared divided by x e to the y plus 2y. And it's totally not that terrible. We've done it before. We could do it again. But there's, in my opinion, there's a faster way that also I think requires less actual thinking, which is kind of nice, right? It's nice to save some of that computation power in your brain for other harder stuff. So here's a different way of doing it. So first, we have to bring everything to one side. So before we can do anything, using the chain rule this time, but our first step, we have to bring everything to one side and have 0 on the other side. Technically, it doesn't have to be 0. You could have any constant, but it's easier to say 0 and always do the same thing. So we're going to bring everything to one side. So from our original equation up here, which you can't see anymore, sorry, we're going to bring everything to the left and say we have x cubed plus y squared minus 7 plus x e to the y equal to 0. What we're going to do is we're going to we're going to say that this is some function of x and y. We're going to call it f of x comma y. And we're just going to use the chain rule. So actually, I need to draw my little diagram. So my function, f is the function of x and y. Well, f depends on both x and y. However, and this is kind of where things are a little bit kind of weird, what are we trying to find? Again, I know you can't see it, but we're trying to find dy dx, which means it's also true that y depends on x. So we also have like this arrow going this way. So if I have, so look at this much simpler equation for a second. My simpler equation is just f of x comma y is equal to 0. Right? I'm just replacing this side with what I've called it. And now we're going to take the partial derivative with respect to x of both sides of this equation. The right side, the derivative of 0 is 0. The left side, we're going to use the chain rule. So the derivative of f with respect to x, well, there's two ways to get there. There's either this path here, so we're going to have fx, plus then there's this path here, which is going to be fy times dy dx equals 0. So now what we're going to do is we're going to say, well, cool, solving for dy dx is super easy, because again, that's what the question was asking us to do, was to find dy dx. So we're going to just manipulate this and say fy times dy dx is equal to negative fx, and then dy dx is equal to negative fx divided by fy. Again, where fx is the partial derivative of f with respect to x, and fy is the partial derivative of f with respect to y. So now check this out. I think it's going to be much easier. For our actual function here, where f is equal to all this, my dy dx is going to equal negative. On top, we're going to have the partial derivative with respect to x, so it's going to be 3x squared plus 0 minus 0 plus the derivative of x times e to the y is 1 times e to the y. Because again, we're taking the partial derivative with respect to x, we're pretending like y is a constant when we do that. And then on the bottom, we're going to get the partial derivative of this with respect to y, which is going to be 0 plus 2y minus 0 plus x times the derivative of e to the y is e to the y. And look, that is exactly the same as what we got doing it the other way. Yes, it's written slightly in the opposite order, but like same thing. So the sum up here is that if you're asked to find a derivative using implicit differentiation, you can use this short, and you're probably like if someone's asking you to use implicit differentiation at this stage in the game, they're expecting you to do this kind of thing. That's why they're asking it. So if you see an implicit differentiation problem, the expectation is to do this kind of thing, where you make sure that your whole equation is equal to zero, and then you just take the partial derivative with respect to the right variable over the partial derivative with respect to the right variable and put the minus sign in front of it. Now, how do you know which ones to take? Well, it's really, really, really not terrible. So let me give you another example and I'll just kind of tell you. So let's say, mm, sure. Let's say we were given x cubed times y to the fourth equal to 1 minus x times cosine of y. And they again said, find, sure, we're going to find dy dx. This one's not that exciting because it's kind of the same stuff. So step one, bring everything to one side. So we've got x cubed times y to the fourth plus x times cosine of y minus 1 equal to 0. And then we're going to call this side with all the stuff on it your f of x comma y. Or f of whatever variables happen to be there. Could be x, y, and z. Could be x, y, z, and w. Could be r and q, right? Whatever people happen to pick. And here's the way I've always thought of it. If I'm trying to find dy dx, it's going to be the negative of fx over fy, meaning whichever variable is on the bottom here ends up on the top over here. Whichever variable is on the top here ends up on the bottom over there. It's always how it works. So it's going to be negative fx over fy. Why don't you all finish that one off? It shouldn't be too terrible. Then we'll do one more. I wrote the wrong thing on top. I wrote fx, right? That's my fx. I think, right? That's, yeah. I wrote the wrong thing on top. That's not right. Should be negative. Sometimes your brain just doesn't want to work there. I'm like that. I wrote the right thing on top. I'm just literally not thinking the right thing. So fx goes on top. It's good to say the words outside out loud. The derivative with respect to x of this thing here is exactly what I'd written there. 3x squared times y to the fourth plus 1 times cosine of y. And then on the bottom goes fy. The partial derivative with respect to y is going to be x cubed times 4y cubed, or as I would probably write it, 4x cubed times y cubed plus x times the derivative of cosine of y is going to be plus x times negative sine of y, or minus x times sine of y. Sometimes your brain just sees the wrong thing. Okay, let's do one more because it can be a little bit more interesting. So let's say we had something like the following. Let's say we have x squared plus y cubed plus z to the fourth equal to 3 times x times y times z. And we are asked to find del z del y. The process is literally the same. So first step, we're going to bring everything to one side. So we're going to say we have x squared plus y cubed plus z to the fourth minus 3xyz equal to 0. And now we're going to treat this as, well, really, if we're finding del z del y, we really don't care about x. So for the moment, we're just going to think of this as a function of y and z. Because x is a constant. We don't care about x. So our del z del y, we could make the same little mapping we made before, but we don't really need to. It's going to be exactly negative fy over fz. So again, whichever variable's on the bottom goes on top. Whichever variable's on the top goes on the bottom. Yeah. So because of the same, so I'll draw the picture again. So again, right, we're assuming that the function f depends on z and y, but also z must depend on y if we're finding del z del y. So then taking the derivative of both sides of this, well, again, we've got this equation, right? We've got f of y comma z equal to 0. And if we use the chain rule to take the derivative of both sides, well, the derivative of the right-hand side is going to be 0. The derivative of the left-hand side, we either have this derivative, which is our fy, or this pathway that gets you from f to y, which is fz times del z del y. And then if you solve for del z del y, you get exactly that. But good to ask. So then we do it. We're going to get, let's see, negative fy is going to be 0 plus 3y squared plus 0 minus 3 times x times 1 times z, or 3xz. And when you look at this part right here, at least at the moment, for this partial with respect to y, I'm thinking of this as like y times 3xz. And the derivative of the y part is 1, and the other part's a constant as far as y is concerned. Similarly, the derivative with respect to z is going to be 0 plus 0 plus 4z cubed minus 3xy times 1. And that's it. All right. That's pretty much all we have to say about the chain rule. It is going to pop back up when we start talking about the directional derivative a little bit. So any questions or comments or homework questions about the chain rule before we move on to more things? Okay. Well, we can always backtrack if we need to. Let's go ahead and look at, well, directional derivatives, but we're going to start with a few things we need for directional derivatives. So I'll point out, we've already very, very limitedly talked about directional derivatives. We've talked about the derivative with respect to x, which is the directional derivative in the x direction, and the derivative with respect to y, which is the directional derivative in the y direction. Now we're just going to expand that to being able to take the directional derivative in any direction from some point in the xy plane. Really, some point in space, but we're imagining like you're on the surface and you're asking from that surface which direction parallel to the ground you're going to travel in. And then how's your slope going to look when you travel in that direction? So I don't have an orange with me today. If I had an orange, right? If you're at the top of the orange, whichever direction you travel, your slope's going to be negative. But if you're like on the side of the orange, traveling, towards you might be a negative slope. Traveling towards me is a positive slope. Traveling that way might be no slope. So depending on which direction you're traveling, it really affects like the steepness of the hill you're climbing or the surface you're on or the hill you're descending. But before any of that, we need a couple things. So directional derivatives. I know I said you should remind yourselves of, but let's remember the dot product. So the dot product. Also sometimes referred to as an inner product or a scalar product. It's the dot product. Again, you really do want to think of it this way, not for calculation purposes, but if you have two vectors, u and v, and the angle between them is theta, we're going to say that u dot v is equal to the length of u times the length of v times cosine of the angle between them. Which again, not very useful formula-wise in that you almost can never actually calculate the dot product this way because you typically aren't given the angle between two vectors. On the other hand, if we have the components of the vectors, like if we know, for example, that u is equal to the vector a comma b and v is equal to the vector c comma d. And you could have two components or three components or more actually, but in this class, usually our vectors are actually like things you could think about being represented in physical space. So usually your vectors are either vectors in 2 dimensions or in 3 dimensions. And the dot product you can calculate as u dot v equal to a multiplied by c plus b multiplied by d. And you're always multiplying the corresponding components together and then adding up the results. So if u was, 3 components and v was 3 components, it'd be the first 2 components multiplied together plus the second 2 components multiplied together plus the last 2 components multiplied together. Yeah. So for example, if u is equal to the vector 4 comma 1 and v is equal to the vector -2 comma 5, then u dotted with v is equal to 4 times -2 plus 1 times 5, which is -3. I would say, in my opinion, there isn't really a good physical interpretation of what the dot product actually means. There's some other things that use the dot product that we'll talk about that makes more sense to talk about. But it's kind of you could kind of say it's like the amount of it's the amount of a vector in the other vector's direction kind of multiplied together. So it's like the amount of v in the direction of u and the amount of u in the direction of v, and then you multiply those two things together. That's not very helpful to think about, I don't think, but it is kind of what it is. We'll say more about that when we start talking about the projection of a vector onto another vector. Which I think, at least I think we talk about projections. Maybe we don't. Maybe I'm totally crazy. Anyway, we'll talk about it if we need to. So let's look at something else. This next thing is very unrelated. I don't think we've ever talked about this, but we do need this one thing for just this one thing we're about to do, and then you can probably forget about it. So I'll talk about the parametric equation of a line. This is really just so we can help define the directional derivative. So normally, in 2 dimensions, we're used to writing the equation of the lines like y equals some mx plus b, right? Like you could totally write the line y equal to 3x plus 2. But I want to point out there's another way you could write the equation of this line, which in 2 dimensions is actually less good, but has a purpose. So let me draw this line for you. Y equals 3x plus 2. I'm not going to draw it very well. So 3x plus 2, something like this. And let's find 2 points on this line. So we've got the point, I don't know, 0, comma 2. And if I let x equal 1, I've got the point 1, comma 5. So here's the idea. Along this line, we're going to imagine a particle traveling. And at time equal to 0, it crosses the point 0, comma 2. And then 1 second later, at time equal to 1, it crosses the point 1, comma 5. And then we could even go further, right? If time was equal to 2 seconds, well, I'd imagine, right, if it's moved, I should say, let me write down some words instead of just saying words. So we're going to imagine a particle. I forgot an important part. A particle moving from the initial point 0, comma 2 to the next point 1, comma 5. At 0, comma 2, it's at time equals 0. At 1, comma 5, it's at time equals 1. at a constant speed. That's the important part that I forgot. So the idea that we're imagining here is that every second that passes, we're going to move over one and up three, over one and up three, over one and up three. So we could write a set of parametric equations describing the x coordinate and the y coordinate based on what time it is or how much time has elapsed. So here's how we're going to, it's not hard to do at all. So here's what we're going to do. We're going to say that x of t and y of t, x of t is just going to equal the value at time equals 0, which for x is 0, plus however far we're moving in the x direction every time we increase time by 1, which is going to be 1. So x is kind of unexciting. It's 0 plus t. Y, on the other hand, is a little more exciting. The y coordinate is, well, at the beginning it's time, or it's the time equals 0, it's 2. And then 1 second later, it's increased by 3, so it's 3t. So this might seem a little bit silly because that equation almost the same as that equation, but that's kind of the idea. And then for any value of t, you could describe a point on the line. So if t was equal to 2, x would be 2, and y would be 2 plus 6, which is 8, which definitely is the point on the line. And then you could do this for a line through any 2 points in 2-dimensional or 3-dimensional space. So for example, just to show you another example, if we had, say, some other line going through the points 1, 7 and 4, 2, it doesn't really matter what you pick to be t equals 0, t equals 1. I usually kind of think from left to right, but really, 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 it doesn't matter. So here we're going to say this is t equals 0, this is t equals 1. We know our initial x coordinate is 1. Our initial y coordinate is 7. And then for the x position, as time increases by 1, the x value increases by 3. So we're going to slap on a 3t. For the y coordinate, as t increases by 1, y decreases by 5. So we're going to subtract 5t. And then you would say that t can be any real number, or t is between negative infinity and infinity. And these parametric equations, because they're parameterized, fully describe that line. Okay. Probably will never need this again other than today. But again, kind of useful. Now, we're going to set that to the side. We're going to come back to it like in a few minutes. Let's look back at the upside down paraboloid that we talked about a couple classes ago. I come back to this example often because it's relatively easy to draw and it's relatively easy to visualize. The f of x comma y equal to 9 minus x squared minus y squared. That downward opening paraboloid looks, I'm just going to draw it instead of trying it. No, it's always kind of a debate how I want to draw this thing. So here's my XYZ coordinate system. And we'll say it looks, let's use a different color. Sure. So that's about 9. And here we go. And then this way, and that way. Then it's coming around like that. Not that we really need to drop it, that intercept right there is 0, 3, 0, because x is 0, y is 3, and x and z is 0. And this coordinate here is 3, 0, 0. And this is 0, 0, 9. And you could label other ones, but I think we've labeled enough. And then we're going to look at the same point we've been looking at before, which is the point 1, 2, 4. So if I go, yeah, we'll do it this way. 1 in the x direction, 2 in the y direction, and then 4 in the z direction. I'm going to end up on the surface. So right there, we're on the level curve where c is equal to 4. So that curve that's going around the outer edge of the circle of the surface, which is definitely a circle, is setting the height equal to 4. So just notably here, if we set c equal to 4, we're going to get 4 equal to 9 minus x squared minus y squared, or x squared plus y squared equal to 9 minus 4. So that level curve there is a circle of radius 5. Let's view it from the top as well. So giving ourselves a different view of what's going on. Here's x, here's y, and 1, 2, 3, 2, 3, 1, 2, 3. My level curve has a radius of a little bit bigger than 2, so it looks like about like, whoosh. Oh, this pen is starting to die. It's too bad. I really like this pen. It keeps dying on me, and I keep putting it back in my pen bag. I should probably just throw it away. Okay, so here's my circle of radius slightly bigger than 2. And over here is the point 1 comma 2. So right there, there's your x comma y is 1 comma 2. We know the z value is 4, so we don't need to write that. So now here's what we're going to ask. Suppose at this point, at the point 1 comma 2 comma 4, we want to move in the direction of, I think I want to change this just slightly. I always feel like it's kind of annoying when I do it that way. Sorry, I'm trying to make it, so I always feel, no, it's fine, it's fine. So we're going to move, so let's write down words. Suppose we are standing at the point 1 comma 2 comma 4, and we want to move in the direction of the vector v equal to, actually, sure, v equal to 3/5, comma 4/5. I should ask, by the way, is this the way that your professor is writing his vectors with the little brackets like that? Or is he writing some other way? Or has he not written any vectors yet? Okay, so this is a typical notation, but he might write it as 3/5 I plus 4/5 j, where I is just a unit vector in the x direction and j is a unit vector in the y direction. So it's 3/5 times 1 in the x plus 4/5 times 1 in the y gives you 3/5 in the x and 4/5 in the y. There's other ways of writing this too, but those are pretty typical here. So basically, we're standing here and we're moving. It's easier to draw it over here. We're moving over 3/5 and up 4/5. So kind of like we're moving that way. Over 3/5, up 4/5. And it's really, I don't want to, I always try and draw it here, but I always feel like it turns out bad. We're moving 3/5 in the x direction and 4/5 in the y direction. So we're kind of moving that way. So I have to think about something for 1 second here. That should be fine. Okay, yeah, all right. So the question. We need to ask a question. So the question is, what is the slope of the surface in the direction that we're moving? And I hope at this point that I've made it somewhat obvious that the slope of the surface depends on the direction you move in, right? If you're standing on the side of a hill, you rotate, right? It's steeper this way, it's less steep that way, it's going down, right? You have options. So your direction of travel definitely determines what your slope of your surface is. All right, so we need one more thing to do this. We need to parameterize the line that this vector is going through. So there's actually a line here, and I've kind of drawn this not perfect. No, that's actually not, I'm crazy here. Sorry. So there's some line. Let's draw it here. So here's my line L. And we're going to parameterize L in the same sort of way. So we have 2 points on our vector, on our line. We have the point 1, comma 2. Let me use more paper instead of trying to jam everything in here. So for our line, which I'll draw again here, I'm not going to draw the other stuff though. Our line, we have the point where the vector starts at 1, comma 2, and we have another point where the vector ends at, well, we're going over 3/5 and up 4/5. So it's going to be 1 plus 3/5 and 2 plus 4/5. That's at time equals 0. That's at time equals 1. So we should be able to do this parameterization without too much trouble. Our line L is going to be given by, well, x of t, the x coordinate starting at 1, y of t, the y coordinate starting at 2, and then in the x direction, we're adding 3/5 every time t increases by 1. So we're doing 3/5 times t in the y direction, 4/5 times t. And that should give us every point on the line. Okay. So what are we trying to find exactly? We're trying to find the slope, aka the derivative of the function. So what we're really trying to find, we want to find the slope, aka derivative of the function f of x comma y in the direction of the vector v. Or in other words, along the line L. Well, check this out. We've set up a chain rule, we didn't even realize it. I know. So let's go back for a second. We have f is a function of x and y, and x and y are both functions of t. Right? We're living on this surface here. We're standing right there. Our height depends on our x and y coordinate, but if we're moving along this line, our x and y coordinate depends on what the value of t is. So we really have this sort of situation where f depends on x and y both depend on t. If you have questions, you're always welcome to ask them. I definitely remember the first time I saw this and taught, because I didn't ever see this when I learned about directional, or if I did, I don't remember it. But definitely when I taught this for someone, I was like, oh, that's really kind of a cool way of thinking about it. I had never really thought about how you have the chain rule showing up here. All right, so check this out. We're now going to find the thing we asked ourselves to find. We're going to find the slope, aka the derivative of the function f, by taking the derivative of f with respect to t. Because we're asking, right, as t increases, right, as you move in this direction, which is really, I know again, which is really this direction, which is really that direction, as we move in that direction, what's our slope? All right, well, we want to find df dt. Well, that's going to be del f del x times dx dt plus del f del y times dy dt. And as a reminder, our function f is 9 minus x squared minus y squared. And our x of t is right there. Our y of t is right there. So check this out. Actually, don't check this out just yet. So what I really want to actually point out here is before we actually calculate this, we can rewrite this. We can rewrite this as a dot product of two vectors. The first vector is the vector of partial derivatives, del f del x comma del f del y. There's a name for this vector we'll talk about in a second. Dotted with the other vector, which is dx dt comma dy dt. Let's actually calculate it now. Del f del x is negative 2x. Del f del y is negative 2y. We do have to plug in the point to actually calculate this part of our calculation here. So we're going to plug in the point 1 comma 2 comma 4. We don't really need the 4 there, I guess, but whatever. Dotted with our dx dt is, well, the derivative of x is 0 plus 3/5. dy dt is derivative, or the derivative of y is 0 plus 4/5. So hopefully it is unsurprising that this derivative dx, or this vector dx dt comma dy dt is just the vector v that we were given in the first place. And then if we plug in our point, we're going to get negative 2 for the first component, negative 4 for the second component. So it's going to be negative 2 comma negative 4 dotted with 3/5 comma 4/5, which is going to give us a value of negative 2 times 3 is negative 6/5 plus negative 4 times 4 is negative 16/5. So it's going to be negative 22/5, or a slope of a little more negative than negative 4. So as we move 1 unit in this direction, we're going to be going down a little bit more than 4 units in the z direction. So our slope is fairly negative. The more important point, though, is what we have right here. So let's actually go back to this for just a second. So what we have here is that the directional derivative of f of x comma y in the direction of a vector, I'm actually going to call it u instead of v, and there's a reason for this, which we'll talk about in a minute here, is given by the following. It's going to be the partial derivatives of your function. It's going to be del f del x comma del f del y dotted with whatever the vector u is. But there's a nicer way of writing this. There's a name for the vector of partial derivatives written in the typical order, right? If your function was a function of x, y, and z, your three-component directional vector here would be del f del x, comma del f del y, comma del f del z, right? Always written in the logical or lexicographic order. This vector here is called the gradient, the gradient vector of your function. So this is equal to, we call this the gradient of f, and it is a vector, and it's dotted with u. And the name we give this is the directional derivative of f in the direction of u. Notice the gradient of f and the vector u are both vectors, and when you dot these two vectors together, you get a numerical value, the slope, the derivative, whatever you want to call it. Now, something we didn't say, but you should be aware of, is that the vector u should be a unit vector. So u is a unit vector. More generally, if v is not a unit vector, then the derivative, the directional derivative of your function f of xy in the direction of the vector v is easy to calculate. You just make v into a unit vector by dividing it by its own magnitude. So it's going to be given by the same gradient of f dotted with, instead of the vector u that's already a unit vector, you're going to transform v into a unit vector. So it's always your gradient vector dotted with the unit vector in the direction that you're taking the derivative in, which is kind of what we've already been doing. Let me show you what I mean. So just as an example of something you already know, what if I said, I want to find the derivative of f of x comma y equal to x cubed plus y squared plus x to the fourth times y to the fifth in the direction of x, which is the vector 1 comma 0, and that is a unit vector. It has a length of 1. I should point out, in case it wasn't clear, this vector up here, 3/4 comma 4/5 is also a unit vector. That vector has a magnitude of 1 because if you square those things and add them together, you get 9 over 25 plus 16 over 25, which is 25 over 25, which is 1. And the square root of 1 is 1. So I gave you a unit vector to start off with. Here, if I asked you this question to find the derivative of f of x, y equal to this in the direction of v equal to 1, 0, comma 0 at, because you do have to give a point you're taking the derivative at, let's make it not too terrible, at say 2 comma 1. Let's do it the way we just talked about calculating. So we're going to calculate this. It's going to be the gradient of f dotted with v. So the gradient of f is our fx comma fy dotted with 1 comma 0. Well, look what's going to happen. Before you even calculate it, we're going to get fx times 1 plus fy times 0. Which makes sense. If you're taking the derivative in the x direction, you should get the partial derivative with respect to just x. So that's what I meant when you already know how to do this, is that we already know two of these directions very well. So here we would just end up getting it equal to, once again, it's going to be evaluated at 2 comma 1. So we're going to get 3x squared plus 0 plus 4x cubed times y to the fifth. That's an x, believe it or not. Evaluated at 2 comma 1. So we get 3 times 2 squared plus 4 times 2 cubed times 1 to the fifth, which is something gross. I don't know. It's 12 plus 32, which is 44. But the point there is that you already know how this directional derivative works in some cases. If you're moving in the x direction, well, your unit vector is 1 comma 0, and the dot product works out just like this. Well, let's ask a more interesting question. Instead of asking, let's keep the function the same. Let's now ask, what is the directional derivative still at the point 2 comma 1 in the direction of v equal to, I don't know, let's make it something funky, like 2 comma negative 3. And even though it's not particularly nice, it's really just a very straightforward calculation after you've done it a couple times. So we're just going to start off by writing, great, it's going to be the gradient of f dotted with the vector v. Not just the vector v, apologies. V is not a unit vector, right? The magnitude of that vector is definitely not 1. So it's v divided by its own magnitude. And I would leave off, like the divided by its own magnitude part, that's kind of like the last part of the calculation, meaning I would put it out in front. So it's going to be my gradient, fx comma fy, evaluated at 2 comma 1, dotted with my vector v, which is 2 comma negative 3, divided by its own magnitude, which is the square root of 2 squared plus negative 3 squared. And that dividing by the square root of whatever that number is, I would leave that out in front. Like I would really rewrite this as, let's see, that's 4 plus 9, that's 1 over the square root of 13 times, let's see, to have enough room here, I should probably use more space. It's always a good idea to use more space here. It's 1 over root 13 times my gradient here is my fx is still 3x squared plus 4x cubed y to the fifth. My fy is going to be, let's see, 0 plus 2y plus x to the fourth times 5y to the fourth, or 5x to the fourth y to the fourth. And we're evaluating that at, we're dotting it with, geez, James, we're still evaluating it. The numbers here are kind of gross. Wonder how that happened. Dotted with 2, -3. So what I'm pointing out here is though, this 1 over root 13, really you can pull out in front. That's not important. The important part is this vector dotted with that vector. So we get 1 over root 13 times this first vector. If we plug in 2 and 1 for x and y, we're going to get 12 plus 32 again. Sorry for the numbers that are not quite so lovely here. Comma, if we plug in 2 for y and 1 for x, we're going to get 2 plus 5 times 16, which is 82. Usually the numbers are a little bit nicer when someone who isn't me comes up with them. So then we're going to dot these two things together. We're going to get 1 over root 13 times 44 times 2, which is 88, plus 82 times -3, which is -246. And then we add them together and we get something like negative something. I don't know, 246 minus 88 is 46, 42, 158. So there's your slope in that direction starting at that point. Again, the idea here isn't too complicated. The numbers are not nice, but the actual like computation is relatively easy to start with, right? It's just your gradient vector, plug in your point, dot it with your unit vector in the direction you're given. Let's look at maybe a nicer example than the one I just came up with. Let's go back to our previous example. No, let's actually not. Sorry. Actually, yes. Sorry. I know I keep going back and forth. So back to our beginning example of our function being 9 minus x squared minus y squared. Let's say we want to find what is the slope. And when we ask this question, you have to be given two pieces of information. I have to give you the point where we're doing this at and the direction we're doing it in. So we want to know what is the slope at the point 1, 2, 4 in the direction of v equal to -3, +1. And I would say I've probably been doing too much writing when I calculate this. So a better kind of more efficient way of writing this out would probably be the following. Let's just find the gradient first. So the gradient of f is the partial derivatives, always in the alphabetical order. So in this case, it's going to be -2x, -2y. And then we plug in our point, not our vector, plug in the point, and we get the gradient of f evaluated at 1, 2, 4 is going to be -2 times 1, -2 times 2. So there's the gradient we're going to dot with whatever vector we're in the direction of. So then our direction as a unit vector is going to be u equal to the vector v divided by its own magnitude. So in this case, that's going to be the vector v -3, 1 divided by the square root of -3 squared plus 1 squared. Or in other words, 1 over root 10 times the vector -3, 1. Apologies for the screen. I'm always happy to clarify something. So then, to find our directional derivative, which we should write as dvf or du, you can kind of use u or v, whichever way you want to write it here. Let's write it as duf. Duf is going to equal our gradient, which is -2, -4, dotted with our direction vector, which is 1 over root 10, -3, 1. And I don't need to rearrange this to still see it the way I want to see it, which is I'm just going to do the dot product first. So I'm going to just think about pulling out this 1 over root 10, and then the dot product is going to be -2 times -3 plus -4 times +1, which is going to be giving me 1 over root 10 times 6 minus 4, which is 2. So we can write this as 2 over root 10. If you really wanted to, you could rationalize this. I don't think that's necessary unless your teacher says it is. If you want to rationalize it, it's 2 root 10 over 10, which becomes root 10 divided by 5. So again, the words we're saying here is that at the point 1, comma 2, comma 4, but now in the direction of the vector negative 3, comma 1, the slope of the surface is going to be positive root 10 over 5. So around 3/5, right? Because root 10 is a little bit bigger than 3. So if we move in that direction, we're going up the slope, but it's not like too steep. It's not like just that. So yeah. All right. What time is it? Okay, we still got a little bit of time here. Um, so I'm going to ask you all to try one here on your own. And I'm going to walk you through it a little bit. So, example. So I want to give you this function. So our function f of x comma y is going to be 5xy squared minus 4x squared y. And our point is going to be the point 1 comma 2. Again, it's a nice point. And our unit vector, and I'm going to give it to you as a unit vector, is the vector 5 over 13 comma 12 over 13. Fun fact, you will often see vectors that look like the components of a Pythagorean triple triangle. Like, maybe your favorite Pythagorean triangle, the 3, 4, 5 one. That's where the 3/4 and the 4/5 are coming from. And here, this is really coming from a Pythagorean triple, which is 5, 12, 13. So this is also has a magnitude of 1 because 5 squared plus 12 squared equals 13 squared. Or 5 over 13 squared plus 12 over 13 squared equals 1. All right, so what I want you to do first is just find the gradient for me. So part A, find the gradient of f. And there's two other parts that you can work on as well. So after you find the gradient, then evaluate your gradient at the point 1 comma 2. Then after you've got that, find the directional derivative by doing the dot product of the two things. I'll give you a couple minutes to work on that. So there's my gradient. It's not pretty, but it's the partial with respect to x, which is 5y squared minus 8xy, and the partial with respect to y, which is 10xy minus 4x squared. And then the gradient evaluated the point. We're just plugging in the point 1 comma 2 for x and y here. So again, it's going to be not super nice. It's going to be 5 times 2 squared minus 8 times 1 times 2, comma 10 times 1 times 2. I'm not writing the times 1 part because we know that multiplying by 1 doesn't change anything. Minus 4 times 1 squared. So it looks like we've got 5 times 4 minus 16, which is 20 minus 16, which is 4, and 20 minus 4, which is 16. I feel like I made a mistake. Maybe not though. So I'm just no, I know what it is. No, I didn't make a mistake. I'm just looking at the work the person who wrote this did. I think they made a mistake, which happens sometimes. Yeah. Yeah. Oh well, it's fine. It's okay. Make mistakes, Grant. So that's all. Does that look right to you all? Right. Okay, good. Right. Cool. If you're looking at Grant's notes, which is what I'm looking at, he did make an error when you wrote this up. I should let him know. But I feel like I see this every year right there. I'm like, oh yeah, I'm looking at Grant's notes. Oh, there's a mistake there. Grant error. Um, Channel does this? Yeah. Okay. So we calculated that. We calculated that. Now we're going to find the rate of change of f at p in the direction of u, or in other words, find the directional derivative of the function in the direction given. So that's just going to be your gradient dotted with the unit vector u. So that's going to be our 4 comma 16 dotted with, if you prefer, you can totally write this vector as 5 comma 12 times 1 over 13. I kind of like to leave the denominator out if it's the same, which it usually is. So then dotting these things together, we get 4 times 5, which is 20, plus 16 times 12, which is 192. I think, let's see. 10 times 16 is 160. 2 times 16 is 32. 160 plus 32, yep, 192. And then divided by 13. So we're going to end up with 212 over 13. Cool. Um, yeah, what time is it? Okay. So what I really kind of want to say though is what's so there's yeah. There's a couple properties of the gradient which I think I actually want to mention right now with the last few minutes we have here. So, a couple properties of the gradient, and then we will depart. Some properties of the gradient. So this is where it's really important to remember our original definition of the dot product. So the gradient, not the gradient, apologies, the directional derivative, duf, right? The directional derivative of f in the direction of u, which we've been calculating as the gradient of f dotted with the vector u. Another way, even though we're usually going to do this as, first component times first component plus second component times second component divided by whatever is to divide by, it's also not unreasonable to think of this as the magnitude of the gradient vector times the magnitude of the unit vector times cosine of the angle between them. Um, and then we can draw a little picture here, right? Here's the direction we're going in. Here's the direction of the gradient. Here's the angle theta. So let's ask a question. What direction u can we travel in to maximize the value of the directional derivative? In other words, what should the angle theta be? So what should theta equal so that the directional derivative equal to the magnitude of the gradient times the magnitude of u times cosine of theta is as large as possible. Well, if we think about this just a little bit, the answer actually is going to be not too terrible to see. So, two things to observe. The three things, this pen is terrible. That's one thing to observe. Two other things to observe. What's the magnitude of u? Well, u is a unit vector. And the length of a unit vector, by definition, has to be 1. So unit vectors always have a length of 1. So this here is always equal to 1. The magnitude of the gradient at whatever point you're at is going to stay as it is, right? The direction doesn't affect the magnitude of the gradient. The gradient is fully dependent on the function, your surface, and what point you're doing it at. But the gradient doesn't depend on what direction you're taking the derivative in. Right? They're unrelated, although related, but like not dependent. So the gradient is just like, cool, there's this thing, which we'll say what it is in a minute. We'll say more about, and then, but what matters is how the gradient's direction and the directional derivative's direction are oriented with each other. So let me ask you all a different question. What angle makes cosine of that angle as big as possible? What's the biggest cosine can ever be? Yeah. What's one of the, I know there's a lot of angles. What's one of the angles that makes cosine of that angle equal to 1? 0. You could say other angles like 2 pi, but if you're thinking about the vectors pointing in the same direction, the angle between them is 0. So the angle should be theta equal to 0. Or in other words, the direction that we travel in to maximize the value of the directional derivative is the direction of the gradient. Because if the angle between the gradient and the direction is 0, that means they're pointing in the same direction. So this is kind of a big deal. The direction of the gradient, or the gradient itself, is the direction that maximizes the value of the directional derivative. Said another way, the gradient points in the direction of steepest increase. Said another way, the gradient's going to be the direction that's the hardest to climb up the hill. So if you are standing on the side of the hill and you ask the question because you're really thinking about your math class, which direction does the gradient point? It's the direction that is the steepest way to go up the hill, which is usually not the way you're going to go up the hill, right? Usually switch up. That's what the gradient is. Said another way, the gradient is the direction that crosses the contour lines perpendicularly, or crosses the contour lines as fast as possible. Because if you're crossing the contour lines as fast as possible, you are increasing your elevation as fast as possible. So I really want that to stay with you, that the gradient is the direction where we're increasing our elevation as quickly as possible. We're crossing the contours. And if you look back at I wish I had a better. Yeah. If you look back at like before, if you look back when we did like the contour lines of the downward opening paraboloid here, but they're all concentric circles. Crossing those lines is exactly perpendicularly pointing directly towards the origin, which is where the steepest part of the mountain is. So it really, really is true that the gradient points in that direction. And then next time we'll talk about what the value is. So when you do travel in the direction of the gradient, how steep is your surface? Well, I'll tell you, the steepness is whatever the magnitude of your gradient is. Which again, if you look at this formula, should make some sense, right? The directional derivative would be the magnitude of the gradient times 1 times 1, right? Because that's going to be 1 and that's going to be 1 if we're traveling in that direction. We'll say it again next week, but I just wanted to give you that preview. But it is kind of neat stuff. All right, that's all we got.